Hey everybody, it's Bruce and the dog on the floor, and today I'm here to talk to you a little bit about the numerical Elixir project. And I'm actually going to work a couple of examples in Axon, the machine learning framework. And the reason that I want to do this is that we've been doing a little bit of work in Groxio in the Julia language, and so far the Elixir language had been previously closed to this type of computing. Well, essentially because the data structures were not conducive to number crunching. But with a little bit of work in this library and some sister libraries, that's changed, and I want to kind of show you what some of that's about. Now, before we dive into Axon and actually build an example or two, what I want to do is actually show you what the NX is all about. Now, this is an umbrella project that has the multi-dimensional tensors and numeric definitions for Elixir, a dataset project called SciData, LiveBook, which is a Phoenix live view framework that allows you to work in a notebook format similar to the Jupyter notebook or to the Pluto notebook or things like it in languages like Python and Julia. And then the one that we're going to work in is Axon. Now, this is a machine learning framework, and it's one that relies on a technique called autograd or auto-differentiation. Now, this means it takes you back to your calculus days where it actually takes derivatives to compute a gradient and then uses those to plot the most rapid path directly to a solution. And so we're going to take a look at a couple of problems in the Axon space. So let's get a little overview of what's happening in here. And so in here you'll find the typical mixed directories. Then you'll also find the notebooks directory. And right now there's only Jose's talk that he's given in the video and the one that he gave at the Lambda Jam. And you ought to see this one populate with a few other notebooks over time. But these are using the LiveBooks that we talked about earlier. But what I really wanted to do is dive into the lib directory and see what's going on inside of Axon. So in Axon, you have some activation functions, and those are functions that are between neural network layers that you see right here. And the neural network layers define individual different types of ways of connecting individual functions, which are called neurons. The activations are a way to make those layers make predictions that are not necessarily linear, so that they can make more complex predictions and converge more rapidly. And then there are things like parameters that help Axon extract the parameters from individual layers and from combined models. And then there's a training API. And unlike some other machine learning frameworks, the training library actually builds in the concept of an optimizer and a loss function, the parameters, your training data, and what's called your labels or your targets. And we're going to actually take a look at what that does. So we're actually going to do a little bit of training in an IEX project, but I wanted to show you first what we've done in terms of the dependencies. So we've included the dependencies for the umbrella numerical Elixir with the individual numerical definitions and things like that, then the extra compiler support in Exla, and then Axon, which is the framework that where we're going to be spending most of our time. And this is actually the piece that has the machine learning model built in. So we're just going to live in IEX. So I'm in IEX in the project that we were in previously. And I decided to do it here so that we could basically do a little bit of exploration. Now, one of the ways that you can also do this is in the LiveBook notebook, but I wanted to save those concepts for another video so that I could basically show what's happening in NX. So what I would like to do is actually try to choose a product or a project that's well understood. And this is the childhood game FizzBuzz. Well, FizzBuzz is a game that has three different properties of numbers, whether something is divisible by 3 or by 5 or by 15. and uses those in a childhood game. So it's a counting game where the first person would say 1, the next person would say 2, the next person would say 3, and so on and so forth. But if the number that you say is divisible by 3, you say fizz. If it's divisible by 5, you say buzz. If it's divisible by both, you say FizzBuzz. And so that's what we're going to implement. And you might wonder why I implement such a toy project. Well, very often what I like to do is build up on the base abstraction so that you could take a very simple, well understood project, and then we could build layer after layer, and you could actually see what each of the layers does. And you don't have to focus on the problem domain so much. You can focus on the platform that you're using to implement it. So it is with Axon, and that's what we're going to do next. Okay, so before we get going too far with Axon, let's briefly talk about what we're going to do. We're going to establish test and training data split across the inputs and predictions. Then we're going to specify a model, which is a neural network split into layers. And then we're going to train the model in a multi-step process that essentially uses a technique called auto-differentiation under the hood. Now we won't touch that code. It's actually been coded for us. And then once the training is done, we're going to verify the parameters that are generated, and then we're going to use them to make predictions. And pretty much every Axon project is going to look something like that. Now let's go ahead and start with creating the data. We require, I'm going to need Axon, and then we're going to think about our data, and we're going to start with integers. But if we can use those integers to actually build some features that Axon can use to make better predictions, our model will evolve more quickly and give us more accurate results. So let's take a look at what that might look like. So let's say I want to build the results of our modular division. And let's just say we have this function, it takes it in and it produces maybe, so we want something that might look like in mod 3, but that's another language. So in Elixir, this is give me the remainder of, say, n divided by 3. And so let's grab a couple of those, right? I want to drop that in, n divided by 5. And then we also, for FizzBuzz, it's 3, 5, and 15, right? That's another way of saying divisible by 3, divisible by 5, and divisible by both. And as long as we provide our FizzBuzz function, as long as we check this one first, then I think we're going to be okay. So let's see, yep, I looked for X instead, didn't I? Okay, so that looks good. And so now let's build this FizzBuzz. Let's build this FizzBuzz function. And so in this function, what I'd like to do, rather than, so if say n divided by 15, if that remainder is 0, then what I want to do is return FizzBuzz. But that's not really going to help me. So what I'd like to do is return a number instead. So maybe it's 0 for fizz, 1 for buzz, 2 for FizzBuzz. So that would be a 2. And I'm going to go ahead and skip a step. What we actually need to do is encode that, right? So it's not a 0, it's not a 1, it's a 3, and it's not a 4. So this first one would be, it's not a 0 probability of fizz, 0 probability of buzz, probability of 1, 100% for FizzBuzz, and 0 probability of something besides those, right? And so let's go ahead and grab another one of these. So if we're divisible by 3, And then that is going to give me a fizz, isn't it? And if this thing is divisible by 5, that's going to give me a buzz. That's going to give me a buzz. I don't know why I thought that was so funny. Actually, it was kind of funny. So true. So if this is true, then pick this clause, and so on and so forth. And if the last one is true, this is going to be an else, right? So 0, 0, and then 1. And then we're going to have to decode this at some later point. Okay, where did that blow up? Let's see. Oh, I see it. Right there, and then we need to do a cond do. Okay. That one, yep. There we go. This is why some of those people actually cut and paste code. I think that's cheating. So I go ahead and struggle through it so you can struggle right along with me. So I could basically say FizzBuzz of 1. So this should be an else. So this should be 0, 0, 0, 1, and it is. And if I did a fizz, that's 1, a buzz, and if I did a FizzBuzz, yeah. Okay, so those are done. And now what I need to do is start to think about, so these are the functions that are actually going to build my training data. So most of the time, what's going to happen is you're actually going to go out into the world and find your training data, and you're going to find the results that it applies to, right? So you might scrape data from MLS or some realtor service to actually find house details and house sales prices, and then scrub the details so that everything is numeric, and then normalize it so everything is between ones and zeros. We've kind of bypassed that by choosing a toy problem, so we don't have to normalize anything. We don't have to restrict it to the right range. We don't have to do anything like that. We can actually go compute our training data and our test data, which is kind of nice, right? So we don't have to do the hard work of the data scrubbing. I know that you already know how to do that in Elixir. You're interested in understanding Axon and the machine learning elements of this problem. Okay, so let's go ahead and say, what is our training data going to look like? This is going to start to use some of those NX features, right? So I mentioned the idea. So I mentioned that we have some features in Elixir that are not conducive for rapid processing. So an example would be the list. So instead of cramming a whole bunch of mutable numbers back to back in memory and allowing changes of every single one of those pretty quickly, what Elixir does instead is implements an immutable linked list. And that's not going to work very well with Axon at all. And the other problem with Elixir is that the numerics are primarily implemented in a way that's not as computationally effective. It's actually built for reliability instead, and it's so we don't want to have some of those features like auto upgrade of numbers and things like that. So what we're going to do instead is we're going to rely on NX to do the numerical computations, and this is actually handled with something called dirty nifs. And with those dirty nifs, we can actually call into other libraries to do that work for us and do it much more efficiently. Okay, so we're going to actually use some of those features. So I'm going to say for n is taken from 1 to 1,000. Give me a tensor, nx.tensor, and give me the mods for that n. think that's it. Yeah, and so this is, you can tell that this is kind of early. It's pretty spaced out in terms of the implementation here. But you can see that the tensor, this is a signed 64. We probably could have reduced this quite a bit by making this an 8-bit integer or something like that. But this has the remainders, 1 divided by 3, 1 divided by 5, and 1 divided by 15. And then the same thing for 2. And then here's that first interesting feature. So with luck, NX will come to identify the zeros in this list because they're the ones that are going to determine when to say FizzBuzz or FizzBuzz. And so at least we hope so. And so we've built a list of tensors, one for each observation, right? And so we have a batch of 1,000 so that hopefully we can train more quickly. Okay, and so now we need a test. And so let's say the test is, let's say for n is taken from 1 to 15, do, and give me the mods of n. Okay, so this is going to take this whole thing and feed it into a tensor like that. So this is a 15 by 3 tensor, and I don't know why, but that seems to be the shape that Axon needs. And so then the next step is to build the actual predictions that go with this data, or the actual values. So let's call this targets. Sean actually likes the word targets because this is actually what we want the system to learn to do, right? So we want it to, based on these inputs, these 1,000 inputs or so that we've created here, we want the first input to create the first input of our targets, and so on and so forth. So this should be a pretty similar beginning, right? So we should say for n is taken from 1 to 1,000. So I'm going to say I want to build a tensor, and we want this to be a list, right? And we want this to be FizzBuzz of n. I think that's right. Let's see. So we want a list of lists, yes, because these targets are often in batches, so we often have one more dimension than you might expect. So I'm going to get one dimension with a 4, and I'm going to get another dimension right here, and that will correspond to the batch, and then another one right here. So that's the FizzBuzz, and remember the FizzBuzz of n is going to give me that already encoded list of ones and zeros that correspond to each output target, right? So, and the reason that we actually shape the data that way with these ones and zeros is that this is a model that's called a probabilistic model, where hopefully each one of those numbers is a number from 0 to 1, and if it's a well-behaved system, and we're going to make sure that it is, we're actually going to make those numbers sum to 100%, which is kind of what we're going after. And that's why we're shaping the data in this particular way. Okay, so we're going to let this fly. So now we have the train data, we have the test data, and we have the targets, right? And so we should probably have the test targets as well. We're just going to eyeball that, or actually we're going to make a friendly prediction. So let's go ahead and pick up with the next phase of our model. So the next couple of steps that we're going to take, we're going to use this data, and we're going to build a model. Then we're going to feed that model and the data into a training step, and that will tweak the model, all the knobs and levers, which are the weights and biases, which are called the parameters of the system. And then we're going to use that to make predictions. So we're going to build the model next. Okay, so here's where we should see some Axon Jiu-Jitsu. So this is our model. This is going to be used to build a prediction. So I'm gonna say, okay, we have an input layer. And so this is actually going to be used to construct our inputs. And we're actually going to pass the shape of our inputs. And since we want to be able to use this model with an arbitrary number of observations, we're going to pass the first parameter as nil, as in we don't know how many batches we're going to provide, right? We're going to make that decision later. And then how many features do we have? Well, we have 3 features. We're going to pipe that much to a dense layer. So in the dense layer, we need to provide a couple of things. How many outputs does this layer have? And actually, what is the activation function that we want to apply? Okay, so let's go ahead and use a nonlinear function called, well, it's based on tangent, so it's tanh. So essentially, these are the inputs that we're passing in, and we're going to pass the training data here. So it's going to be 1,000 batches of size 3, and each one of those is a feature for mod 3, mod 5, and mod 15. And then we pass it into a dense layer, and this is a matrix algebra version of Wx plus b. And if that sounds like the formula for line, that mx plus b that you learned in junior high algebra, that's exactly correct, right? That's exactly what the dense layer does, but it actually is going to look more like a network because it's going to use the rules of linear algebra to expand out this layer. And so we'll look at the parameters that are in here, but there's going to be a bunch of them in there. And then we're going to need another layer, right? Because this is going to produce 10 outputs. So let's go ahead and shrink those outputs to the number of outputs that we expect from this thing. Well, how many do we expect? Well, we need to be able to predict FizzBuzz, FizzBuzz, or something else, right? FizzBuzz, FizzBuzz, or else, right? Which is really a 4-tuple or a list of 4 integers with, if it was else, it would be 0, 0, 0, 1 with probabilities, right? So we're going to say that this is 4. And for the activation here, I want to use a activation layer called softmax. So softmax is basically a way of using a bunch of sigmoid functions, I believe, to take a layer and turn it into something that looks probabilistic, right? Something that sums to 1 where everything is between 0 and 1. And that's going to be great for us. So let's let that fly. Okay, so what happened? 1175, so somewhere around here after Axon. Okay, so axon.input, open, close, yep, axon.dense, and then 10 with activation. Oh, there we go, axon.dense, like that, yeah. Okay, yeah, so now we could tell the shape of each individual piece of the layer, right? So this is nil by 3. Well, if we pass in 1,000, it's going to be 1,000 by 3. And then that next layer is going to be 1,000 by 10. And then the 10, since this is effectively, looks sort of like a broadcast, not in the index sense, but in that we're going to call tanh on all the inputs in the layer as it passes on through. And then we're going to pass everything into a dense layer with 4 outputs, and we're going to normalize those to probabilities with softmax. And so we mentioned knobs and layers. Well, the input layer isn't going to have any knobs and levers because this is effectively the data, and we don't want to change that. This is a malleable layer, right? This has weights and biases that can be tweaked. This is 3 times 10 or 30 weights. And then we're going to add on a bias, which is a vector of 0 to 9 or a size 10, right? And we play the same game here, right? So 10 times 4 or 40. And then so this is a flatter layer, right? This is 10 by 4. So we're going to take that 4 dimension and we're going to add on biases that are that size. And then we take the softmax, which doesn't have any parameters, right? So every time that we run through the training, it's going to produce a better set of parameters. And then based on those derivatives that the framework knows how to create with the AutoGrad functionality or AutoDiff functionality, it's going to basically build a loss function, plug in those knobs and levers as variables, and then it's going to try to predict a version of those that essentially reduces the gradient in the right proportions. And that's a pretty cool thing. I'm not going to get into the math of how that works in this talk, but it's going along well. And so we have really 3 more steps. First, we need to do some training, right? Then we need to make a prediction, and then we need to clean up the prediction a little bit. So let's do all of that next. Okay, here we go. So now we need to do the training. And the training is basically going to give us the training parameters and the optimizer state. We don't really need to track that, so let's leave that alone. I'd rather have the real estate. And so let's start this thing with the Axon. So we want an Axon training step, and this thing is going to take the loss function first. So this is going to be kata cross entropy. So effectively, this is a loss function that works well with categories. And since we have categorical data, so it's going to categorize my numbers into 1 of 4 categories. And if it picks the wrong category, we don't really care how far, once a choice is wrong, it's wrong. And if the numbers climb too much, we want to bring those into range. Whether we are in the 2nd position and should have been in the 1st, or we're in the 3rd position and should have been in the 1st, those should be pretty much should be punished pretty much in the same way. So, and then I want an optimizer. So let's see what's available. Let's see. So how about yes, let's use this version of the Atom optimizer. And let's give it a relatively low rate. See if it likes what I'm doing so far. What did I miss? So there's the, oh, I do need a model here, I think. Yeah, and you can see that this is actually just building the tuple that effectively is going to result in the data structure that the training needs, right? And so now we need to do an Axon dot. Remember, we talked about that training, and you could probably guess what function that we're using. So we need to train it, and the data that we need to pass. Well, we built that training data, and then what were those? So we built the train. And then we built the targets, yeah. You see me slip into pirates there? Targets. Yeah. Okay, so targets, and then we want epochs. Let's just do 10, because remember, there's a good chunk of data that's in there. So, and we're going to use I think that's the default, but I'm not sure. So, and then we want to log some of them. Yeah, I think we're going to skip that logging step. I might be sorry, but I think we're going to be okay there. So Let's go ahead and let that fly. Okay, yeah, so now I'm going through all these epochs. And so I should have these parameters. Yeah, so you could see that this is the, remember we had the weights of that first layer, which was 3 by 10. And then we had the biases of the next layer, which is 1 by 10. This is excellent, right? And then the weights of the next layer, which was 10 by 4. And then the biases of that layer, which was 1 by 4. So these are in the right shape. So I should be able to make a prediction now. So I should say axon.predict. And I need the model. Well, and we also need to feed it the parameters. And then what do we need? We need the test data, don't we? Okay. Yeah, so let's see how we look. So this is going to be, yeah, so let's see if we can actually, if we could actually feed this in. Let's go ahead and actually try to, so let's feed that to, that doesn't help me at all. So, yeah, what do I want to do? I want to do, let's build a function to do. I think that's probably the best way to do this. So I'm going to say predict. So I'm going to make a pretty prediction. So if you take a function, now what did we just do? We just did an axon.predict, and then we did a model, and then the params. And then now we have to restructure, build a tensor with the batch that we need, which is mods.n, right? Right. And so do I need another close there? And then that's going to give me a list of them. So I need to pull out the 0th one. And then I need to feed that into nx.argmax. So if I could say predict dot 1, yeah, and so I get 3, which is else, right? And 2 gives me a 3, and then what is the next one should be fizz, and it is. Okay, but this still isn't very pretty, right? So I probably want to do like a convert function. So I'm going to say function of, and I want to get like a label and an index. Right? So the label is the 0, 1, 2, or 3. And then I want to basically, I want to take an array of words with fizz, buzz, FizzBuzz, or else. So I'm going to pipe that thing into enum.at. And then grab me the label. And then, oh man, this is messy. Okay, then it's kernel.or. And then I would pass the index. Right? Okay. So then I could do something like this. Axon.predict. Right? And then I got the model, params, and the test. Right? And then I can feed that into, so make sure that I'm getting something out that's nice. Yeah, then I could feed that into nx.argmax. So I want to process all of them at one time. What does that give me? Oh, no, that just could be, oh, but I can do one axis, can't I? So axis. So I'm going to do it along, is it 0 axis? No, yeah, because that's wrong. What I really want is along that axis, right? So that's else, fizz, else, buzz, fizz, else, fizz, buzz, and so on. So that's correct. But we could take that. Oh, yeah. So this is cool. So I could pass that to index.to flat list. Yeah, now we're getting somewhere. enum.width index and then offset by 1, right? We want to start at 0, and then the enum.map, and then pass our function, which is, what do we call that? Convert. Oh, you're killing me, Elixir. Oh, there it is. Look at that. Ah, look at that. 1, 2, fizz. 4, buzz, fizz, and so on and so forth. Then we are done, right? And so let's review what we've done here, right? So the first thing that we did was we prepared ourselves by using the machine learning library in Elixir Axon. Then we built some functions that allowed us to prepare features, and then some functions, a function that allowed us to build training data, right? And normally we're going to gather training data from the real world, right? And then we tested it a few times, and then we built our training data, and this is essentially the observations. And this is essentially the labels or the predictions based on those features, those observations. And then we essentially had the targets, and we had a target for each prediction that we wanted to make for each batch, right? And then we built our model. In our particular model, we had an input, one dense layer with an activation, another dense layer with an activation. The last activation, this activation basically helped us normalize data and give us a nonlinear prediction. And this activation layer made it look like a normalized prediction. And then effectively we trained, right? And when we trained the system step by step, one entity after the next, Axon worked its magic. It computed a gradient and used that gradient over the loss function, which in this case is categorical loss entropy. And we took the gradient of this with respect to the parameters, to the weights and biases. I know it's a lot to take in, but there's a lot of papers on this, or you could join Groxio. And then there was an optimizer, and the optimizer codified our approach to actually using the autodiff to actually solve the problem, right? After we defined the parameters, we actually ran the training step. And we got parameters out. Then we could use those parameters to make predictions. And the whole rest of the time, we built a function to actually smooth out the way that we make predictions in the real world. All that remains is I take those predictions, load it into a model, and I don't have to do any more training. Then I can make machine learning predictions and put them on every single street corner block. And so that every child can have a nerves hub that plays FizzBuzz with them. I'll leave out the rest of those details to you. But that's a really cool thing. We can apply this same approach to other categorization problems where we have definable inputs and a loss function that can objectively determine the distance from the truth. That's exactly what machine learning is for, and that's an excellent thing. If you want more of the same, you can take these journeys with us. Go ahead and go to grox.io, and you can subscribe, or you can explore all of our free content as well. From Bruce and the dog on the floor, this is Groxio Learning.